Welcome to this lecture today about an introduction to Python. So Python is going to be the coding language in which we're going to build all of our numerical computations. Both computations in terms of forward problem solving, in other words, where you're given a, let's say, governing equations or a system that you want to simulate, but also Python will act as our engine for machine learning algorithms and machine learning software, things like PyTorch, which allow us to do data-driven modeling very nicely. So Python is going to be this environment in which we're going to do all of our programming. And in fact, what we're going to walk through is a bunch of examples of how you would build the key structures you need, and it's going to be specifically vectors and matrices. And what will also be provided is quite a few number of notebooks, computational engines, computational notebooks for you to play with and build code. Okay, so let's get this thing started. So this is a very basic introduction. So I'm not going to do anything sophisticated here except for talk about very specific applications of what we want for Python, which is going to be towards scientific computing and towards machine learning. So that's it. Python itself is a very broad and general language for doing many, many things. And so we are only touching on a very small subset of what is available for Python to do. Okay, so first of all, getting Python. So one way to do this is to go get the distribution at anaconda.com, and you can actually basically go onto this website and download installation of the Python software architecture. So you would just simply go here towards an individual license, and you would click that. What it's going to give you now the option to do is once you have this, you can download that code, just click here, and this was actually going to go through, and it's going to actually start building a local installation of the Python package on your laptop or desktop, or wherever you happen to be working. So this is the first step, is to get Python installed. There are, of course, many other options for computational engines, including MATLAB, Julia, C, Fortran, but we're going to do everything here. At least all the examples going to show are going to be based out of Python. Partly because, really because of two reasons. One, it's an open source distribution, which means everybody would have access to this just by this free installation. But second, as we move into data science and machine learning, the Python ecosystem has some of the largest collection of code base available to us as users through GitHub. So we can clone people's repositories and have their code base ingested. Most of that code is written in Python, and this is why we're going to install this specifically. So you would go to this, you would install it, and go through that procedure locally on your computer. And then once you have that done, you can actually double-click the Anaconda icon, and what's going to typically pop up is something like this. You can, of course, do all of this from a command line window if you'd like, but you can also just double-click the icon, and what will come up is something like this. Your ability to basically open up different software architectures or different programming pipelines. So we're going to focus on here is the Jupyter notebooks. And for instance, you can also open VS Code, Virtual Studio Code environment. So I typically recommend, if you want to build really nice code base, VS Code is actually a really great way to build your code in. But Jupyter notebooks are a great way to sort of do interactive computing. They're very flexible, easy to use. They load into a browser very nicely, and it's a very nice platform for doing basic programming and interactive programming. But if you're actually building larger code bases, you may want to move over to something like VS Code as your platform for programming. But it does give you a lot of options, and so the Anaconda distribution is actually quite nice that way, to give you such a broad collection of tools available for you for doing computing. Okay, so once you have that, we get to what we really want to do with all of this. So your entire world in programming, at least if you're doing what we want to do, which is going to be scientific computing and machine learning and AI, is everything's going to be framed in terms of taking data or simulations, which means we're going to work exclusively with vectors and matrices almost entirely throughout this in our overall work effort. So vectors and matrices is how you organize all of your data and all of your computations. So it's important that you know how to manipulate them well, what are the properties of these vectors and matrices, and how you do this within a Python environment, because most of your work effort will be in manipulation of these vectors and matrices that you create to be using and building tools with. So first of all, let's talk about what a vector is and talk about what a matrix is. So one way to think about a vector, it's just a really skinny matrix. That's one way to think about it. So I've given you two examples of vectors here. This is a column vector in which the data or numbers are arranged vertically. So that's one way to arrange your data. A vector can also be a row of numbers, okay? And that's a row vector. So we have column vectors, we have row vectors. A matrix is an object which has a given number of rows and a given number of columns. So for instance here, this is a 3x3 matrix. So it's 3 rows, 3 columns. So depending upon what you are doing in your application, almost everything you're going to be aiming for is to put all of your data or all of your computation organized into typically a set of matrices and a set of vectors. Okay? And the reason I said that, vectors are just skinny matrices is because in the column vector, what this is, it has a single column, and a row vector has a single row, whereas a matrix can have, generically we refer to them as an m by n. So m rows, n columns, okay? And so we want to be able to manipulate this because it'll be the basis of all of our computations. So first of all, we want to start with some Python coding. So once you've got Python installed, let's go ahead and make some vectors and matrices. We're going to start off with a simple thing first, which is in Python, we're going to go ahead and make ourselves some vectors. So here, for instance, is a set of code that's going to make for us some row vectors. So I can make row vectors in different ways. So here in this first one, x1, I just give it square brackets, and each number is separated by a comma. So what this is going to do for me is make a single row, and it's going to have 3 components, each component separated by a comma. You could alternatively write this as np array. Now you have parentheses and then square brackets, and then you have the numbers, again, separated by commas. Or you could even do something like this, np matrix, right? The matrix object or command is a little bit broader. You can have multiple rows, multiple columns, but here what we're doing is putting in a single row, which is in this square bracket structure here. These are all equivalent. In fact, you can display these just by the display command. And what this actually gives you then is this row vector right here, 1, 3, 2. So this is the simplest thing to do first, is to be able to make vectors, to be able to make matrices and then manipulate them. So this is, in some sense, a very simple example of how you would make these. You can instead make a column vector, so you may stack them vertically, your numbers. And of course, there's different reasons why you would make columns or row vectors. It's really important you understand whether you made a row vector or a column vector. Okay, because oftentimes when we're doing matrix manipulations, which include taking inner products or matrix multiplies, which we will talk about, when you do that, you have to understand whether you have a row or a column vector. So let's go ahead and now make a column vector. So we can again use the matrix command or the array command. Here, x1, np matrix. Now notice what I do here. Each row is square bracketed. The comma says go to the next row, and the next row. Now, since it's a column vector, there's only one column. For each row, there's only a single column, and so that's why you only have a single number in here. I could, of course, make a matrix and have multiple columns, but then, of course, now it'd be a matrix and not a column vector. You can also use the np array command, and again, same kind of structure. And if you display these, they just give you that vector right there. So now it's a column vector of 1, 3, 2. You've arranged the data vertically versus horizontally, and it's really important that you keep track of what you are doing. Okay? So an easy way to check to see what you've actually done is you could take this vector here, x, and say in Python, say print, and then in parentheses, x dot shape. And that will actually tell you the shape of this vector or matrix. So it'll tell you how many rows, how many columns it has. So it's a nice thing to have in mind. You can either display it or you have print the shape, which gives you actually row column space that you have working with. So this is a way to make vectors. Pretty simple. And then you can either make rows or columns. You often get to choose how you want to arrange your data. And so you can choose it and arrange it in rows. You can arrange it in columns. And so the flexibility and the decisions are actually up to you depending upon how you want to be using these in an application. All right, so now let's go ahead and automate making some vectors. And so now we're going to use this command called arange. So we're going to use the np command. So np is coming in is calling in what's called numpy. And if you go back a few slides, I said import numpy as np. So np is calling this numpy structure, which we're using here. So np calls from this library. And here, when we do this arange, I can go from 0 to 10, okay, in steps of 1. In fact, I'm not going to 10, I'm going to 10.1. Now, a really important thing to understand about Python, it starts to index off of 0. So the first component of a vector is the 0th component. This is different than, for instance, MATLAB or Fortran, where you index the first component is 1. So understanding that about Python is really important because you have to start indexing off 0. And so what this is going to do for us is actually going to make for us a vector going from 0 to 10 in steps of 1. And the reason I went to 10.1, it doesn't actually, if this actually went 0 to 10 in steps of 1, it would stop at 9. But since it goes to 10.1, it goes all the way to 10. The next step would be 11, which is past the 10.1, it doesn't print it. Okay, so it does not include that last step. So it's also very important you understand. So that first vector here in this arange goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If I had stopped this at 10, it would have actually gone to 9 and not included 10. Okay, that's that first vector. Let's talk about x2 here. x2 now is np arange. Again, start point 0, end point 11, and what this says, take steps of 2. So now it's going to go 0, 2, 4, 6, 8, 10. 11 is the big number here, right? So it's not going to go past this, which would be 12 would be the next number. It does not include it, so it stops at 10. So this now makes a vector going from 0 all the way to 10 in steps of 2. So you have the way this arange works, the beginning point, the end point, the step size. That's the structure of how you would program this. You can do fractional steps here. This goes from 0 to 1.2 in steps of 0.2. So this is going to 0, 0.2, 0.4, 0.6, 0.8, 1. And it's not going to land on this last spot, which is 1.2, even though I had to take steps of 0.2. Okay? So if your last point is where it lands, it does not include it in the vector. Next one is steps going from 0 to 9 in steps of 2. Again, 0, 2, 4, 6, 8. Once you're past 9, doesn't include it, so that's what that would give you for this vector. And then finally, if I don't include the increment, it's assumed to be 1. So this one here, the last one, goes to 0 to 5. Since I didn't put the increment at the last comma here, then it's going to go in steps of 1. So it's going to go 0, 1, 2, 3, 4. The next one would be 5. It doesn't include that one. If I had put 5.1, it'd go and include the 5. So just keep that in mind, both the indexing off 0 and the fact that it doesn't include the last point. So if you tell it to go to 5 and it lands on 5, it will not include 5. So just have these things in mind because they become really important in your management of your data streams and your computational schemes. Okay? Indexing and keeping track of your indexing is going to be really critical almost everything you do. And this is where the largest number of errors occur, is because people don't have the right mapping out to the indexes that they need. All right. Let's now make a matrix. So we were playing around with vectors. Now we just generalize this concept, and here is our first matrix A, which is an NP array. And notice I've got the parentheses on the outside, brackets for the whole structure, and then within each bracket is each of the rows. So here's the first row, second row, third row. So when you make this, what it's going to do for you is construct this matrix right here. Okay? So once you've constructed this matrix, the other thing that we often will do is start manipulating it. We're often generating matrices directly from our data sets, and so we often store them as matrices, or often the generalization of a matrix, which is a tensor. So in other words, instead of having rows and columns, it can be an n-dimensional array. So you could have, in fact, 5 fields, and you could make a 5-dimensional array or a tensor, which would store all the data, okay? And so regardless how you do this, we're going to just stick to matrices, which are rows and columns. We often want to manipulate and extract key pieces out of this data set. So let's talk about how I would actually go in and interrogate this matrix and pull out key features. So let's look here at x1, what this is. What I'm going to do here is go to A, 1, 2. So it's looking at row 1, column 2. Remember, we start indexing from 0. So when I say row 1, remember that we started counting from 0. So there was row 0, 1, and then 2. Same thing with the column space. We started column 0, 1, and 2. So when we look at this matrix here, notice what we're going to do. We're going to go down here to row 1, right, which is the second row, and then column 3, which is indexed by a 2 there. So we're going to pull out here that 7. In fact, that's exactly what we do, is we pull out the 7 through that indexing. So again, remember, always start counting from 0. And if you switch programming languages, like for instance to MATLAB, this is where you make a lot of big mistakes can be made because MATLAB is indexed starting from 1, and this starts indexing from 0. Okay. Now let's look at the second line of this code, which if you look at it here, it's A1, colon. So what it's going to do, the colon means grab everything there. So A1, so this goes to, again, the second row of this matrix. The colon means grab everything. So in other words, it's going to grab from the second row all the numbers, 5, 6, and 7. And so what it's going to create for us is a row vector, 5, 6, and 7. So that colon becomes very important. So I can take this matrix and pull out entire rows, entire columns, or individual numbers. And this manipulation process is going to be critical for everything we do in computing. And of course, who's in charge of keeping track of everything? You are, as the code developer. So you have to really understand how you're accessing all your data in this flow of information. Let's go to the last one, which is A, 2. So this says, okay, go grab all the rows in comma 2, which means it's the third row. Third column. So this is the third column here, the 2, 7, 1, that's right there. So it's going to say grab all the rows there, which is, so I go to that third column and grab it, and this is the vector that I have out of that system. So these are very simple manipulations, but they're actually they're the basics of almost everything you're going to do in terms of writing code and building out computational tools, both in terms of scientific computing applications where you're solving some equations, but also machine learning in terms of managing your data, keeping your data, learning how to manipulate your data for ingestion into some algorithms. So this is a very basic structure, very basic coding intro, and everything focused on vectors and matrices because that's actually where everything's going to happen. All right, let's talk about some other key ideas of vectors. One of them is this idea of a transpose. So I can turn a column vector into a row vector just simply by the dot t. So I'll take a vector, column, turn it into row, or it'll take a row, turn it into a column. So the transpose command will just simply flip a row vector to a column and a column vector to a row. And that's how you would use this. Very simple to use, okay? So that 2, 7, 1 up there, if I took that as my vector and I transpose it, it's now a row vector, 2, 7, 1, okay? You can do this also with, in Python with complex numbers, and this is very important here. So when you do this with a complex number, here it is. So if I do a transpose of this, what's actually going to happen, right, you would think that you would just simply lay it on its side, but the transpose does one extra thing. It turns this into a minus sign. So you have to be very careful that it does, typically what it does is not only transpose, it does complex conjugation, so you have to watch out for this. This command, then if you don't want to change the sign of that the complex value, you have to make sure to keep track of that so that you aren't turning your imaginary numbers negative unintended when you're just doing a transpose and you just want to take a vector or its column and turning it into a row. Okay. So that is some really basic structure that we have available to us. Notice that all we did in this, we talked about how to build vectors, build matrices, manipulate them, and extract things from them. And again, one of the key operations there is the transpose. We can lay vectors on their side to make them from columns to rows and vice versa. And so these are kind of the very basic building blocks we're going to need to do almost everything throughout this course in terms of building out architectures and programming. And it's very important that you understand how to do these manipulations because all of your data, all your scientific computing is going to go through these vectors and matrices as we go through it. And so your organizational skills here become critically important to write good code.